Good morning and welcome back to all of you to the second day to our conference. I don't think we need many introductions. Most of us saw each other yesterday, so we know what it's all about. And I'm happy that you have found your way, and the weather is better today compared to yesterday, just like I promised yesterday evening. I heard there was a good after party last night as well. Some of you participated in that, so it's good that you have come back. By the way, if there's any opportunity to take the seats closer to us, that'd be great. But I'm not, pressing that on you. But just bear in mind, we'd appreciate if you do that. A couple of things before we begin with our first panel. I just wanted to remind you about this Slido option that we have. By the way, there was a lot of interaction between the audience and the speakers via the questions yesterday. We did not manage to answer all of those questions, obviously, but the organizers have committed themselves to archiving all of those questions and answering them, not today, but perhaps in a couple of days, and we'll send them out in the overall list of the participants in the conference. So it makes sense really to get engaged and either to use the opportunity to ask questions, address the questions straight on to the members of the panel, but in any case they are not ignored even if they're not answered straight away. So keep that coming. So just go on the website slido.com, enter the event code, and it's very easy to do that. It's redundant for those of us who were here yesterday, but some of the people are new, so please do use that opportunity. Having said that, I'm looking forward very much to the continuation of the conference, because we're now switching to the adaptation sort of segment of the whole debate. And before we switch to the adaptation debate, we want to find out what actually the prospects are and what is the newest data and how the picture looks like, particularly in this region of ours. So our first panel will consist of 3 presentations. I'm not sure whether we will have an opportunity to have a lengthy discussion because of the time constraints, but nevertheless, let me introduce you to Dr. Martin Stendal. He's representing Danish Meteorological Institute. A warm welcome to you. We will have also representative from Bjerknes Center of Climate Research from Norway, Dr. Ellen Viste. She will be joining us via video link. We hope that works. Always, crossing our fingers that technology functions well and good. And we have Svetlana Anishkevicha. She's representing the Latvian Geology and Meteorology Center, where she is head of climate and methodological division. A warm welcome to you as well. So we begin with you, Dr. Stendal. Please give us an impression of what are the climate change scenarios and impacts in our region, please.
Thank you very much. Good morning, everybody. And let's just jump into the whole thing. I'm very glad that I can report to you about the assessment of climate change in the Baltic region. There was a first one a couple of years ago, and we recently finished a second one. I will come to that in a moment. If we talk about climate change adaptation, it is important to know what we are talking about. If we are talking about climate change, you also need to talk about climate. And I will give a very quick look through this. I excuse already beforehand, this will be quite a number of transparencies, so probably we can only just jump through it. But I think it's important that everybody gets an impression what we are talking about. So let's just jump into that. So before we talk about regional climate change, we have to say a word about the global context. So if we cite the last Ipcc report from 2013, the next one is in preparation now, it says that warming of the climate system is unequivocal, and we have since roughly the 1950s observed many changes which, so as far as we can judge it from, for example, instrumental observations, have been unprecedented, mainly in terms of warming, that means temperature, but also the retreat of snow and ice and sea level rise. So if you look at the graphics here, temperature changes in the Arctic are quite obvious. Now the question immediately arises, of course, what causes these changes? And people have been thinking about that for quite some time, of course. And if you look at the view graph here, you can see lots of tiny orange lines. You are not supposed to identify any individual of them. These are 51 model runs where the climate models have been driven, have been forced by all factors that might affect temperature. That is natural factors like variability of the sun, or as you can see at the lines here, there have also been a couple of volcanic eruptions in the 20th century. And then there are man-made changes, mainly, of course, the emission of greenhouse gases. And as you can see here as an example for the 20th century, the model curve follows the observations, which are given in black here. Sorry for the German comment. Follows them quite closely. On the other hand, if we only look at the natural factors, so solar variability and volcanoes, we can obviously not reproduce the warming in the last third of the 20th century. So that's, of course, a strong argument about anthropogenic forcing. Now, coming from global to regional, if we have a look at the Baltic, actually it quickly turns out that we have to look at two parts, the north and obviously the south, which, as you can see here, I think I have to put it into my hand. As you can see here, they are quite different, where the north is mainly consisting of large forests, the south is relatively densely inhabited, and we have subarctic climate in the north, but rather mild winters, at least for the latitude in the south. Now, I am one of the authors of the second assessment on climate change for the Baltic Sea region. This is a kind poor man's Ipcc report. Poor man's in a sense that we are not talking about global climate, but only about climate in the Baltic Sea region. It resembles the Ipcc report in that we only have taken into account peer-reviewed literature, and there's quite a bit of them for the Baltic Sea region, I can guarantee you. So we looked through that and compressed that into a book of something like 550 pages, and no less than 141 authors from 12 countries have been participating. The whole thing has been driven by a scientific steering group. The results of the book itself has been peer-reviewed, and the good thing here is it is open access. So if you happen to take a photo of this QR code, or if you look on springer.com's homepage, you can easily find it. You can buy it for 140 euro, but you can also download it free of charge. And actually 50,000 people have already done that. So we have 25 chapters, some of them dealing with long-term climate change, with more recent climate change. That means the last 200 years, roughly, since we have instruments, and of course future climate change. And these are the two I will be talking about today. And some extended summaries in all the languages around the Baltic are planned, but have not yet been produced. Now let's look at temperature. This view graph here shows temperature over the last 140 years since we have reasonable instrumental observations. The north in blue and the south in red. And as you can see, there's a warming trend, but it is different from season to season. It's also different regionally, but in particular, if one goes a step back and looks at the overall picture, we can see that there has been warming in the Baltic region. If you look at rain, and actually at any other variable, things become more complicated. There is a signal, but the signal is not really clear. That does not mean, let me just point that out, that does not mean that there is no climate change. It just does mean that the variability, the internal variability is so large that it is very difficult to find a climate change signal if we are looking at a region which is as small as the Baltic is. So we have some signals in precipitation here, but actually the large decadal variability dominates everything. And if you look at this one here, actually 2 15-year periods is a little bit on the short side where we can see something. All in all, again, if we go one step back, we can see there's a slight increase over the 20th century, which makes sense because warm air can bear more water vapor, and we would expect that there is more precipitation. But that's only the overall picture. If you look at wind speed, something which is of course also important in the Baltic Sea region, we can again, in particular in winter, see huge variability from decade to decade, but there's at least no obvious trend in storminess. We can elaborate that a little bit if we count the number of deep lows. In this case here, that has been done for southern Sweden. Just let me say that again. This is all taken from the peer-reviewed literature. We haven't written anything, or haven't made any research on that ourselves, but just compiled the existing literature. So here's an example from Sweden. And again, we have decades which have been very stormy, in particular the late 1980s and 1990s, the most recent one. But there's hardly any obvious trend to see over this period, and this goes back more than 200 years. Other things are a little bit more clear. If you look at if you look at river ice and lake ice, it becomes clear that the ice break-up and freeze-up dates have changed. So the icy season has become shorter, and the duration of ice cover has decreased, and also one can measure that the thickness of the ice has decreased. So that is more obvious. And if we look into the ground, the black lines here give us the depth of the active layer. That is the layer, if you have permafrost below, that is the layer which seasonally thaws in summer and then freezes again in winter. Below that layer, the ground is always frozen. So if it gets warmer, the active layer becomes thicker. And here are a couple of examples from subarctic Sweden, and we can see that this is indeed the case. The depth of the active layer has increased, which is also a clear sign for warming. We can look at water temperatures, and here we can see that we have detectable warming in the Baltic, not only at the surface but also in the deep water. And this seems to have increased in speed since the 1990s. Again, if you look at sea ice cover in the north of the Baltic Sea, there's huge variability, but here one could argue that the trend is visible, and there have been less years with much ice recently. And in 2007, 2008, we had the winter with the lowest ever recorded ice in that time series here. And then we can look at sea level. Here, of course, we need to take into account that there is a large land uplift in parts of the Baltic. This has been subtracted here, so this shows us only the increase in sea level, and here we are on the order of something like 20 centimeters over the last 120 years or something like that. So the rate, which is on the order of 1.5 millimeters per year, is roughly comparable with the global rise. For this, there are two possible candidates. One is the expansion of seawater as it gets warmer. The other one is melting of ice on Greenland and elsewhere. But this is mainly the expansion of the water because of warming we see here. So if we talk about, now we have set the scene for what we have observed so far, and from that we can, of course, deduce future changes by looking at climate models. However, we have to keep into account that prediction is very difficult, as Niels Bohr said, so we cannot predict it. Actually, what we can do is we can project it. That's something different. We take a large number of models, get some results, and then can span up a very probability space, saying that we expect with a probability of, for example, 95%, that the changes in temperature will be between something else. It's not a prediction that it will be like this on the 21st of June 2047. That's important to keep in mind. So if we do it anyway, there's of course another difficulty, because we don't know what, for example, the Chinese will do in 50 years in terms of emission of greenhouse gases, as we simply don't know what we will do next year. So a couple of scenarios have been made up, as you can see here, and this looks a little bit irritating. Here we give the global temperature change and its range from different models. And this, of course, depends on the emission of greenhouse gases. And if you look at this curve here, actually it turns out that it's not so complicated. This graph shows us the total amount of carbon or carbon dioxide which has been put into the atmosphere and the associated temperature change. So this is, for all these scenarios, roughly a straight line. So the whole question actually reduces to how long can we go on and emit greenhouse gases like mad. So the green scenarios, that's probably why it's just given in blue here, stops already in around the 2050s, and the red one, where we fire everything we have, follows approximately the same line, but then goes on, of course, and ends at a global temperature rise on the order of 5 degrees. So it's roughly following a straight line. Now, in order to tackle this problem, we have to make ensembles of models. So we do that, we take a large number of climate models. These are global models. You can see something like 19 models here, and they show quite some different evolution here. This is an example for northern Sweden. And these are global models, as I said, so the distance between two grid points is on the order of 100, let's say 100 kilometers. That's, of course, too coarse, so we cannot really use that for regional climate forecast or projection. So what we do is we take the data from these global models and then drive regional models with them, which go down to a grid point distance of, say, 5 kilometers. The price we have to pay is, of course, that we have to run two models, namely the regional model and the global model that gives the data over the boundaries of the regional model into the regional model. And now, of course, we can imagine all possible combinations of global models and regional models. That has been done. And if we do that, we come out with something like this here. So this is a temperature change for summer in the Baltic Sea region. And let's say we have 25 of these model combinations. Then we can take those where the temperature increase is lowest, which is on the left side, and we can take those where the temperature increase is highest on the right side, and we can take the median, where there are as many colder as warmer. And if we see that, if you look at that, there's an increase on the order of 2.5 degrees in summer temperature. We can do the same for winter. Then the increase, even if you look at the median, is larger. So we are talking on something of the order of maybe 4 or even 5 degrees. This is a clear signal, of course. If you look at precipitation, then the whole thing is less clear, but actually one can deduce that in general it becomes drier where it was already dry before and becomes wetter where it already has been wet beforehand. That means wetter winters, drier summers. But also, if you look at the high percentiles here, we could look at the 99 percentile, the wettest 1%. It turns out that the most intense rain events become even more intense, even if it else is drier. So, if we look at wind, this is more difficult to say. There's no obvious trend. So, even though one might get the impression that the wind speed has increased, this is actually, or is going to increase, that's actually not really backed up by the data. Another thing is runoff. Here we can see that runoff increases, and because we have less snow, it peaks earlier. So this is a more clear signal. Concerning sea surface temperature, there's also a clear signal. We can expect that the temperature, or the water temperature increases by something on the order of, let's say, 4 degrees, and in the deep water, which is not so deep, of course, in the Baltic, on the order of 2 degrees. And this is rather uniform across all seasons. So this is also a clear signal. There's also a clear signal for sea ice extent. If you look at the left one, which is sea ice extent under present-day conditions, and the other one is at the end of the 21st century, just as an example. So sea ice in the Baltic will have disappeared except for the far north on average, of course. And there is also a projected increase in sea level, which is on the order of half a meter in the southern Baltic and a slight decrease in the northern parts of the Baltic Sea. Again, this is both because the glacial isostatic adjustment after the last ice age, so land is rising. If we only look at sea level increase without taking that into account, then we are somewhere on the order of half a meter everywhere to the end of the century. So, if we look at impacts here, I will try to make that very short indeed. So, one point we look at is that we have changes in air pollution, but this can actually rather be traced back to changes in emission and political measures to do that than to climate change. So that means, of course, that future developments will depend strongly on policy developments, which is something we cannot say much about as scientists. If you look at land, it's clear we have a longer vegetation period and we find a northward migration of species, and along with that an increase of the area covered by forests, at least in the north. And generally, climate change, of course, is only one of many observed factors which is important in a densely populated area like the Baltic, which at the same time is rather small, so that also natural variability has a big effect. And it's obvious this was a point in the assessment report that this has consequences for all kinds of things like tourism and how much heating we need to use, but this is clearly out of the scope of this talk here, so I just jump it over. And then, of course, it turns out it is important, or can we find out if this regional change is due to human influences or are there other causes? Well, the case is rather clear if you look at the global plane. It's not because of the large variability, it's not so clear if you look at small regions here. And again, it turns out that the changes in aerosols will have a major effect. Again, this points to politics. And it turns out that also changes in land use and land cover in a region as small as the Baltic is will have a detectable effect. So if I just am allowed to sum that up, we have clearly observed increases in temperature, that's both for land and for the sea, and connected changes in things which have to do with that. That means freezing and melting days, ice cover, also coastal erosions, permafrost, length of vegetation periods, and so on. It's much more uncertain in precipitation and wind, storminess. That does not mean that it doesn't exist, it just does mean that we have problems to detect it from these data sets here. We can expect further warming and further sea level rise. We have to take into account land uplift, I said that a couple of times. And the anthropogenic climate change is only one man-made factor. But in a densely populated area like the Baltic, we also have to look at, for example, land use changes and things like that. That means, of course, further research is necessary, in particular to address the size of the changes due to land cover change and due to aerosol change. Thank you.
Well, thank you very much, sir. There's a very quick follow-up before you return here to the panel from the audience. Why Ipcc should be so trusted as a source of information on climate change? Is that something you
yes.
want to tackle?
Yes. Actually, that is because it is the best we have. That's one can quickly explain that. It's the same thing we have used here at this assessment. So, if we look at the peer-reviewed literature, that means people try to publish something in well-renowned journals like Nature or Science, or maybe not so well-known, at least for the laypersons. That means these papers are reviewed by other scientists, by their peers. And more often than not, they say, oh no, we don't want to see that. Actually, that makes the whole thing rather too conservative than too progressive. But having people who understand something about that look at their colleagues' work, that's probably the best thing we can do. And that takes away as much as possible any subjective factors. Now, in writing such a report, it's not only that we only look at peer-reviewed literature, then we have, as I said, 141 scientists sitting together and saying, okay, shouldn't we formulate this like that or that like this? And there also needs to be found an agreement, again, between people who are specialists in their particular fields And by this, I'm actually confident that this is the best we can do in order to avoid personal biases.
Okay, thank you very much, Martin. If you could come back to the seat here, Martin.
Yeah.
Yeah, here. Thank you, Martin. If you could return here. We will have, after we have heard from the others as well, we will come back to discussing some aspects of what you told, because I found some of the stuff you said, I mean, very informative and fascinating at the same time. So a lot of things to discuss, but we also want to hear from Dr. Ellen Viste from Norway. Okay, do you hear me? Is our link working?
I can hear you. Good morning.
Okay, good. Okay, then I'll give you 10 minutes or so for the presentation, and let's hope the line stays in place and we hear you well. Okay, go on, please.
Thank you very much, and good morning, everyone. I'm Ellen Viste from the Bjerknes Center for Climate Research in Bergen, Norway, and I'm going to talk a little bit. I'm going to show you a few examples of how we use climate models in our work. We only have one planet, and you've probably heard that before in the context that we should take very good care of it, which of course we should. But for the climate scientists, it means something else. It also means that we don't have anything to compare with. At least we don't have an equal planet to compare with. So we have to use computer models. The computer model is the lab of the climate scientist. So with a climate model, we can, for instance, turn on or off the greenhouse effect, or we can have 5 different worlds with different temperatures, and we can see how that influences other parts of the weather. I'll start with going back to the past. I'll also talk about the present, how we use this in the present and the future. And now I'm getting a little bit back.
Can I interrupt you, please, for a second? Is it possible to have your microphone closer to your mouth, because it's really difficult? Well, that could work. And if you could lower the microphone as well. Yes, talk to me, please, now.
Does this work better?
Oh, this does work better. Thank you very much. This is perfect.
Okay.
That's
So,
lovely.
I'm sorry. Does this mean that you did not hear anything about what I said, or did you hear something?
Okay. Once again, the microphone closer to your mouth. The microphone. Just the microphone. Yes. Can we try like this, please?
Do you hear me now?
Whoa. This is great.
Wow.
Yes.
Then we'll
please
try that.
retain the microphone where it is. Go on, please. Sorry for interrupting you.
So, can I ask you a question first? Did you hear anything of what I said, or?
We tried to understand, but we actually gathered very little from what you said, so the sound wasn't too good. So if you could very quickly summarize it and then go on.
Yes. I was talking about how we have to use climate models in order to, because I mean we use climate models as a lab for the world. We can't really experiment on the real world because we only have that one planet, so that wouldn't be possible. So we're using computer models instead. Do you hear me now?
Yes.
Yes. Okay, then I'll continue. So we can use computer models to understand more about the future, the past, and the present. And I'll go through a few examples of that. I'll start with going back to the past. So this you actually got a glimpse of with the previous speaker, but I'm going back to it. So during the last century, the global mean temperature has increased by about 1 degree. So this shows the observed temperature from 1880 up until today. We clearly see that it has increased, and that's what the observations can show us. They can show us the change, but they cannot just show us why this change has occurred, which is why we need computer models. The models do a pretty good job of recreating this change. The red curve here now is from one of these climate models, the Norwegian Earth System model run by my colleagues. And we see that this follows the observed curve pretty well, and it ends up at the same level today. But still, to actually understand what has happened, we need to take things apart. Two things that are known to influence climate is the sun and volcanoes. So solar activity varies, in some periods making it warmer, and in other periods making it colder. As for volcanoes, they throw a lot of particles in the air, into the air when they erupt, And these particles act as little mirrors reflecting the sunlight, meaning that volcanic eruptions cool the Earth. And if we look at the thin curve here, that is, now my colleagues have run the climate models without any changes except these natural changes. We see that there are quite some variations from year to year, especially as a result of volcanic eruptions. But in the end, I mean, the result is more or less the same at the end now as it was in the beginning. So if it were only for natural changes, the world would not be warmer today than it was in 1880, as we see that it has actually been. Then we can turn it around. So what they've done here is that they've turned off the natural changes. They have not included solar activity or volcanoes, but they've looked only at changes in the greenhouse effect. You see this thin gray line on top here. And with doing only this, we actually overshoot. So if we look only at the greenhouse effect, the temperatures should be higher than they actually are today. So something must have acted to cool the Earth. In this run, they have disregarded the natural changes in solar and volcanic activity, and they have not included the increase in greenhouse effect. They've included only changes in air pollution, so these tiny particles called aerosols. But different kinds of aerosols act in different ways, but as a total, the changes here have acted to cool down the Earth. So if this had been the only change, the world would be colder today than it was in 1880, which we know it's not. This is the same as I now showed you in the beginning. So the red curve is still the models. The models now, they include all these different effects, and we see that that's necessary to reproduce this change. It also shows that the greatest temperature increase by far has been due to increase in greenhouse effects over the century. So this was an example how we use models how you can use models. You can turn on and off effects, and that's how these models work as a lab. You can make little experiments. So that was the past. For future, I mean, climate models are at least much known as for projecting future climate change. And then we run into a different problem, because we know how much greenhouse gases we have released into the atmosphere, but we have no way of knowing how much we'll emit in the future. But the climate models work the same way. So the experiment will then be introducing different amounts of heating related to these greenhouse effects. And we can then do this for different emission scenarios from society. You may have seen this figure before. It's from the Ipcc's last assessment report. So the upper curve here is a curve for high emissions. So it's a temperature increase we see with a high emission scenario. And the lower curve is for a low emission scenario. The lower curve would keep us within the 2-degree target, but it also would require quite large changes. We would need to cut CO2 substantially. Yes. So I presented now an example of the past and the future, but as much climate scientists actually use climate models to understand how weather and climate works in the world today. And it's related to the same thing, that you can turn on and off things, and then you can see how these mechanisms, then you can see the mechanisms, you can see what actually matters for making changes and how the weather works. As an example, for instance, you may have heard of the El Nino in the Pacific. This is a phenomenon in the Pacific. It's a heating of the Eastern Pacific Ocean, but it also affects the weather over large parts of the globe, especially in the Pacific. So I have colleagues at the Birka Center who work with just turning on and off the El Nino in the model and then see what happens to the weather. And that's a way to find out how this does influence the weather and what really matters. I also have colleagues, for instance, who would remove sea ice in the north, in the Arctic, and then they would see how that would influence the weather. Climate models can also be used to study storm tracks to see how the lows, whether they go far up north and hit western Norway or go further south into Europe, and how weather in different parts of the world affects each other. So all in all, climate models are an invaluable tool for finding out how weather and climate works. But and to solve the climate problem, of course, we need climate models, but the climate models themselves are not enough. So what is surely needed is for climate scientists and the people who use the data to cooperate to find out what is actually needed and how the models can be used to serve society. And during the last years, cooperation between stakeholders and the climate scientists at the Birkner Center has become more and more important. That is something I hope we'll see even more of in the future. Thank you.
Well, thank you very much. Well, thank you, Ellen, very much for introducing us to the intricacies of climate science and modeling. I'm afraid, though, that the line is not that excellent for us to continue that conversation for too long. But in any case, thank you very much for taking the time out and joining in our conversation today. Thank you very much. Okay.
Thank you.
Thank you. So. Right, so we go on, and then we'll throw some things into the discussion. I invite Svetlana Anishkevich now I don't know whether there can be a particularly Latvian look at those issues which are, global and regional in character, but nevertheless, please do go on.
Good morning. My presentation will be a bit more technical, and it will be about localization of climate change scenarios for Latvia for further adaptation applications. And as it was already mentioned in introduction, I will tell a little bit about Ipcc 5th Assessment Report. Intergovernmental Panel on Climate Change, or Ipcc, on regular basis releases assessment reports, and at the present moment the newest one is the 5th assessment report that states that global warming will continue during the 21st century, although the severity of the simulated changes varies from model to model and mainly is dependent on the evolution of future greenhouse gas emissions. Therefore, the future evolution of greenhouse gases concentration was represented as three alternative forcing scenarios called RCP, or representative concentration pathways. Under RCP 8.5 scenario that represents strong climate changes, emission continued to increase throughout the 21st century, while two other scenarios forecast that the emission will decline during the century. And based on these scenarios presented in the 5th assessment report, the newest and the most comprehensive climate model ensemble became available, or CMIP-5 global models. In Latvia, in order to analyze climate change, we analyzed 5 main meteorological parameters, such as mean, maximum, minimum air temperatures, precipitation, and wind speed. And in order to provide objective future climate scenarios, several CMIP-5 models were used, and to be precise, 28 models were used to model air temperature and precipitation, 25 models to model maximum and minimum air temperatures, and 24 models for wind speed. In order to localize climate models, several steps must be done. And firstly, observation data are needed, and data are needed for all the analyzed meteorological parameters, having long enough time series and all around the country. Also, quality control should be done in order to provide a qualitative analysis and to avoid different inhomogeneities in datasets. Later, spatial interpolation should be done, taking into account different parameters that influence weather, such as continentality or elevation. And since climate models are outputs of numerical calculations, it is necessary to provide correspondence to real climate. Therefore, bias correction must be done. And as an example of bias correction, on the plot there is presented scenarios of maximum air temperature for the RCP 8.5 scenario. On the left plot there is past values, and it can be seen that the observations are with black line plotted, with the blue one is modeled scenarios but uncorrected, and the red line represents modeled data but corrected. And it can be seen that modeled data, uncorrected modeled data, does not fit real past climate, while the corrected data fit perfectly. Therefore, only after bias correction it is possible to estimate future climate changes. And after the localization of the models, it is possible to derive different meteorological parameters. For example, it is possible to calculate monthly multimodal changes in maximum air temperatures with taking into account the uncertainties among the different models and the internal natural variability. It can be seen that both scenarios forecast strong positive changes in maximum air temperature, and the scenario RCP 8.5 is clearly bimodal with two peaks at approximately 5 to 6 degrees in January and August. All the previously mentioned results this year were published in climate change analysis tool that allows interactively visualize climate and climate change, download the data, and also read the report of the project, and also to summaries in Latvian and English. Even though, for example, mean air temperature changes for 3-5 degrees may seem small, climatologically it's a very significant change that in foreseeable future will substantially influence all different sectors of economy, for example, forestry, agriculture, engineering, etc. Therefore, it is important to create climate monitoring adaptation system, climate change adaptation monitoring system, and which main goal will be to evaluate and track the climate change impact on different domains. This system will consist of two different parts, where first one is climate change monitoring that will be performed by Latvian Environment Geology and Meteorology Center, and the second one is based on adaptation indicators that were developed by the experts from different sectors. And one example of such adaptational indicator is an indicator that describes the vulnerability of recreational winter activities. Such index consists of two parts, where one describes climate influence, and in this case, for example, number of frost days or average snow cover depth in winter. The second part is sensitivity and society resources. In this case, percentage of population of Latvia who take part in recreational winter activities. Further, it is possible to estimate vulnerability of the sector, and if at the present moment there is a low vulnerability, then in future experts forecast that this sector will have high vulnerability. And shortly, this is it. Thank you.
Thank you very much. Yes, thank you. I actually saw yesterday that it attracted a lot of attention, that application that visualizes the climate change and models. A lot of people play around with the tool in the action area. So we don't have a lot of time for questions, but nevertheless, let me introduce something from the audience here, but I'll go on with my own question first, and then I'll look into the Slido thing. Martin, my question to you was, well, when I was observing your presentation, I had the impression that we are a region that is actually, for some reason spared from the worst effects of global warming, right? So from the climate change, in the sense that we had the Fiji ambassador yesterday, right? And obviously his country's story is much different, being in Southern Pacific. So it seems to me that a lot of effects are actually, to some degree, offsetting of climate change. I mean, if it's warmer, the trees grow faster and accumulate CO2, and if it's warmer, we use less heating, therefore emit less CO2 and stuff like that. So would you agree to say that, well, we are a bit spared from the worst effects as a region?
Does this work?
Yes.
Okay, great. Well, I wouldn't say spared. Compared to the Fiji Islands, of course, yes. We are in a, let's say, somehow lucky position here. For example, that we won't expect major problems due to sea level rise because of the glacial isostatic adjustment. So the land rise as a reaction on the end of the last ice age. There are a couple of, I'm a little bit reluctant to call it advantages of climate change, but I agree if you say in other regions which are on the edge already now, it is much worse. But we should also take into account, I don't want to lead that into the field of politics, but we cannot expect that we are just sitting here having relatively overlookable effects of climate change, and people elsewhere have it much worse, and they just stay where they are and wait until they die. This will probably not be the case, so we also have to have a look at the political implications this unequilibrium in climate change effects will have in the future.
Right, and my last question to both of you, and I think this comes from the audience. I actually like this one very much. So so basically, the context is this: that I mean, the climate debate is not really over. I mean, it might be over among scientists for the most part, but in the politics and in society, it's not over. So you as scientists as well, you do encounter people who say, you know, oh, what are you telling me? I don't really believe all of that. And so one member of the audience is saying, can meteorologists, scientists define short arguments? I mean, what is the short version of the argument you're presenting to someone who's saying, I mean, this is all bogus. I mean, why are you asking? What is the short argument you're saying to Donald Trump, right? Who's not really. So I don't know whether you can persuade Donald Trump about anything, but what is the argument you would use, the short one? I'll give Svetlana here the first. What is the short version of your argument? Why is this really a problem?
Okay, it works? Oh, well, I would say that at the present moment, climate changes and global warming is the only model that really describes what's happening right now, and it's really explaining the real world. Therefore, it is better to adapt and take it in and have it in mind than just ignore it and do nothing.
All right, Martin.
Yeah, I would say it in one sentence, but actually I have to say another sentence before that. This other sentence is, the climate debate is not over, it has just begun, for sure. So the sentence I would be telling Donald Trump, probably I would not be able to convince him, but climate change is real, and we can see that if you look at the difference between what comes in from the sun and what goes out into space again. And this last one is modified by the amount of greenhouse gases we put into the atmosphere. And as long less goes out than comes in, the Earth will warm with all the consequences I and the other people have tried to show here.
And there's a clearly identifiable effect of human,
Definitely, yes.
All right. Okay, thank you very much for this panel. Thank you for... Okay, good.